Conservation of mechanical energy. Both conservative and non-conservative external forces do work on objects. So the total work done on an object is the sum of the work done by conservative external forces and the work done by non-conservative external forces. The work kinetic energy theorem tells us that the net work done on an object by external forces is equal to the change in the kinetic energy of the object. The kinetic energy of an object is equal to 1/2 times its mass times the square of its speed. Combining these three expressions, we get a new expression for the net work done by external forces. If the only conservative force we're dealing with is the gravitational force, then the work done by conservative external forces is equal to m times g times the initial height minus the final height of the object. We found this when we talked about gravitational potential energy. We will now substitute this expression for W sub c into this expression to get this result. Now we will solve this for the work done by non-conservative external forces. Now we expand out the last term on the right-hand side. We can see now some familiar expressions. This is an expression for final kinetic energy, this for initial kinetic energy, this for final gravitational potential energy, and this for initial gravitational potential energy. The work done on an object by non-conservative external forces is therefore equal to the change in the kinetic energy of the object plus the change in the gravitational potential energy of the object, when the gravitational force is the only conservative force. The total mechanical energy of an object is equal to its kinetic energy plus its potential energy. So far, we have only talked about gravitational potential energy. Later, we will see that there are other forms of potential energy that contribute to the total mechanical energy of an object. We just found that the work done on an object by non-conservative external forces is equal to the change in the kinetic energy of the object plus the change in the potential energy of the object. We can rearrange this expression so that we group the final kinetic and potential energies, and we group the initial kinetic and potential energies. This term now represents the total final mechanical energy, and this term represents the total initial mechanical energy. If the work done by non-conservative external forces is equal to 0, and all the non-zero net work done on the object is done by conservative forces, then E final minus E initial equals 0. In this case, E final equals E initial, and we say that the total mechanical energy is conserved when the work done by non-conservative external forces is equal to 0. If we substitute in the expressions for kinetic and potential energies, we can see that a very useful result of this is that the sum of the kinetic and potential energies of an object at any point in its motion is the same if total mechanical energy is conserved. How do we use the principle of conservation of mechanical energy when working problems? First, we need to identify the conservative and non-conservative forces acting on our object. We can only apply this principle if the work done by non-conservative forces is equal to 0. Remember that a force acting on an object in a direction perpendicular to the object's motion is not doing work on the object. If conservation of mechanical energy can be applied in the problem, next choose the location where the gravitational potential energy of your object will be equal to 0. It's usually easiest to just choose the lowest position of the object's motion. Finally, set the final total mechanical energy of the object equal to its initial mechanical energy. Remember that the total mechanical energy is equal to the sum of the object's kinetic and potential energies. Let's look at an example problem. I coast down a hill on my bicycle without pedaling. The hill has a vertical height of 7 meters. At the top of the hill, I have a speed of 1 meter per second. Ignore friction and air resistance and find my speed at the bottom of the hill. Let's see if we can apply conservation of mechanical energy to this problem. First, we need to identify our conservative and non-conservative forces. We have gravity as our conservative force. We're told to ignore friction and air resistance, which are the non-conservative forces that would apply here. So the work done by non-conservative forces is equal to 0, and we can proceed using conservation of mechanical energy. Next, we need to choose where my gravitational potential energy will be equal to 0. Let's make this my H final position at the bottom of the hill. My H initial position is at the top of the hill, and we are given that the hill has a vertical height of 7 meters. So H initial minus H final equals 7 meters. We're also given my initial speed at the top of the hill. It's 1 meter per second. Now, what are we looking for? My final speed at the bottom of the hill. So we need an equation. So now we set the final total mechanical energy equal to the initial total mechanical energy. Total mechanical energy is kinetic energy plus potential energy, so we'll substitute that in. Next, to get this in terms of our known values, we'll substitute in the expressions for kinetic and potential energies. We see that mass is in each term of this equation, so we'll cancel it out of each term. And next, we'll take the steps to solve this equation for V final, since that is what we're looking for. Now we can plug in our known values for V initial, G, and H initial minus H final. And finally, using our calculator, we solve, getting a value of 11.8 meters per second. So remember, in these problems, first, make sure that the work done by non-conservative forces is equal to 0 so that you can apply conservation of mechanical energy. Then choose where the gravitational potential energy of the object will be equal to 0. Then set the total final mechanical energy equal to the total initial mechanical energy and solve for your unknown values.